Fast and efficient space travel is essential to maximize our efforts in outer space, whether they be for exploration or one-day colonization. With space travel, you need to carry all the fuel necessary for your trip with you. There aren't any places where you can refill your tank. Using rocket fuel is not the best way for ships to make long trips through space.
Rockets work in space by using Newton's third law of motion, that every force has an equal and opposite component. The fuel the rockets carry is burned and gas is expelled from the rocket. The gas and the spacecraft act on each other and propel the rocket in the opposite direction of the gas. Most rockets use liquid or solid propellants, both of which take up a lot of room on spacecraft.
Like we said before, rockets need to carry all the fuel they need with them from the start of their journey. This means that currently the weight of spacecraft are 95% fuel at launch. With all this weight added on, it's not efficient or practical to use spacecraft that rely on thrusters and fuel tanks to go distances much further than the moon. So how can we make space travel more efficient? And how can we go further and faster in space? A large, thin, reflective structure called a solar sail is one possible solution to these problems.
The general concept behind solar sails is using the momentum of photons from solar radiation to provide force that would cause a continuous acceleration to a solar sail. The sail would need to be very reflective as to cause the photons to reflect backwards and transfer their momentum to the sail. This momentum provides a constant acceleration, which would eventually cause the spacecraft to travel at very high speeds.
With a constant push from just the sun's photons, a solar vehicle could potentially get a velocity up to 90 kilometers per second. This is more than 10 times faster than the space shuttle's orbital speed. With just the feeble rays of sun at Earth's radius, solar sails could reach 12 kilometers per second in just 6 months and get to Pluto in only 5 years, compared to previous efforts that took 12 years. If we launched a solar sails probe, we could catch up to Voyager 1, which has been traveling for over 20 years, in only 8 years. This is just with photons, not counting the momentum solar sails already have when they ascend into orbit. If we were to add a laser magnetic beam transmitter, the top speed could be 30,000 kilometers per second, 1/10 the speed of light.
Solar sails can be used to perform a variety of tasks in outer space, both in Earth's orbit and beyond. This can be utilized as space weather warning systems by orbiting the Earth for long periods of time. They can also hover in orbit and support satellites for communication, and the lack of need for propellant makes them an efficient way to carry probes and other spacecraft much farther than traditional spacecraft. When orbiting a planet, the sails can tilt to orient the force from the sun onto its velocity vector and ensure that the sail and its satellite can stay in orbit. Similar to sailing a ship, the sail adjusts to the wind to stay on the desired course. Their use of solar radiation as a means of travel provides a continuous push as long as the sun's photons can reach them.
There are 4 main parts of a solar sail. The first is the spacecraft bus. It's in the center and comprised of a navigation and steering sensor, the flight computer, radios and antennas for communication, solar arrays, and the power system, as well as other scientific instruments. Also in the bus is an active attitude control system, which is essential for a sailcraft to achieve and maintain a desired orientation. Steering vanes are small sails at the end of the booms that can rotate and cause the whole sail to turn in the desired direction. Sails, the most important part, are the large, thin, reflective sheets that are pushed by the sun and can be greater than 100 meters on one side, often made of a plastic polyamide called Kapton that is coated with a layer of aluminum to give it reflective properties.
Kapton is a polyamide film that is only 5 microns thick, and it is very lightweight. It is formed from the synthesis of an aromatic dianhydride and an aromatic diamine. Dianhydrides and diamines are structures that have 4 acyl groups and 2 amino groups respectively. Aromatic structure means that the molecules form rings with multiple double bonds. This structure causes them to be very stable molecules, resulting in bonds that are easy to make but very hard to break. Kapton is often made of monomers pyrometallic dianhydride and 4,4-oxydianiline because of their reactiveness, which is a result of their high electron affinities. The process of forming a polyamide is a series of simple reactions that have a complex relationship and can be significantly affected by the reaction conditions and the mode of monomer addition. Higher concentrations of monomers produces a polyamide with a higher molecular weight. The molecular weight affects the density and tensile strength of the polyamide, so the choice of monomer and its concentration can significantly alter the properties of the Kapton sheet. This relationship is important because Kapton needs to have a high tensile strength while also having a low density to reduce the amount of force needed to accelerate the solar sail.
Kapton and other polyamides have very strong interactions between different polymer chains. Within each chain, 2 types of monomers bond together, donors and acceptors. Donors have a lot of nitrogen groups that lead to excess electrons, and acceptors have a lot of carbonyl groups, which take away from its electron density. Donors and acceptors bond to level out the uneven charges between them. These chains stack on top of each other to form layers, and donors and acceptors bond in this direction too. This leads to strong, stiff bonds in all directions. This structure is very important in influencing the properties of kapton.
Kapton is a good insulator. It has a long lifespan and a tensile strength of 231 MPa at 23 degrees Celsius. It also has a low density of 1.42 grams per milliliter. Because of the charge transfer in and between polymer chains, everything is held together tightly from a molecular level. Strength is necessary to withstand the solar wind pressure present in space. Kapton is able to maintain these properties over a temperature range of negative 269 to 400 degrees Celsius. This is a major issue with solar sails because exposure to direct solar radiation can cause much higher temperatures. When used in solar sails, the aluminum coating provides the reflective properties needed for movement. Kapton could potentially be pierced by meteoroids from time to time, but the effect on the sail's travel is minimal due to the large area. Above all, solar sails require a flexible material that is lightweight and can cover a large area, as the amount of sunlight received is proportional to the acceleration.
Kapton's high resistance to temperature change leaves few viable processing options, with digital laser material processing being one of the best methods. This involves the use of digital information to shape a material by a high-powered, precise laser that can cut and process kapton very effectively, with minimal damage to the edge of the sheets. Aluminum coating is applied to kapton film by framing machines once the film has been cast the right width. Usually, the coefficients of thermal expansion between the aluminum and film don't match, so the use of filler materials in chemistry can change the CTE for aluminum to match the kapton film.
Both the structure and the processing greatly impact kapton's properties. The way bonds form at the molecular level increase tensile strength in the material, necessary to withstand high speeds and solar pressure even over a large area. While forming the kapton sheets, finding the right balance of concentration of monomers is essential to creating a high enough tensile strength, but also keeping the density to a minimum. Each of these properties contribute to kapton's usefulness in solar sails, but a few of these properties take away from our ability to use it. Kapton's relatively low temperature range wouldn't work well in outer space, and currently we would need a sheet of kapton the size of Texas to travel large distances in a reasonable amount of time.
As a material to be used in outer space, kapton's main advantage is its high tensile strength. This property allows it to be made into sheets with very large area, which is essential to its purpose. The more area covered, the more sunlight is received, and the faster spacecraft can travel. In addition, its lightweight nature promotes faster travel in space. To achieve and surpass our goals for space travel, the use of kapton in solar sails might be the answer we've been looking for, but we're not quite there yet. Once kapton's drawbacks have been dealt with, maybe we can achieve interstellar space travel.